All right, welcome to Unit 4 on probability, random variables, and probability distributions. In this video, we're going to focus on topic 4.3, an introduction to probability. I'm going to just kind of go over the quick idea of basic probability, what the definition of probability is, and how we can actually start to begin to find probabilities. All right, first, all probability starts with what we call a random process. A random process is any situation where we do not know the outcome. If it wasn't for a random process, we wouldn't have probability. I mean, there are so many things in our lives that we encounter where we don't know what the outcome is going to be until it actually happens. And if it wasn't for that, if everything was predictable, if we knew what everything was, if there was no variation in our lives, then we really wouldn't need probability because we would already know the answer to everything before it happened. But that's not the world we live in. So probability all begins with understanding a random process. Random processes can be pretty basic, like rolling a die, right? I don't know what's going to happen when I roll a die. Tossing a coin. Before I toss the coin, I don't know what's going to happen. Spinning a spinner with 5 colors on it, don't know what's going to happen. I don't know the outcome. Picking 3 boys out of a classroom with 12 boys and 14 girls. Boy, I certainly don't know what's going to happen. I could get Maddox, I could get Mike, I could get Tommy, I can get Justin, I can get Clinton. I mean, I don't know the outcomes of who 3 boys are going to get picked. Or random processes can even be a little bit more complicated. Like, how long am I going to take a shower for tonight? Every night I take a shower, how long is it going to be? I don't know the outcome. When I get out of the shower, I don't know how long it's going to take. Same thing, time to get to school. I don't know how long it's going to take to get to school. I know that it might take 3 minutes. It could take 15 minutes, but in the morning when I wake up and I get in my car to go to school, I don't know how long it's going to take. When you approach a traffic light, I don't know the outcome, red, yellow, green. Even the idea of a sample proportion, right? So think about this. What is the proportion of smokers in a sample of 500? Gosh, before I actually go and ask the question, do you smoke or not? I have no idea what the answer could be. But these are all ideas that going into these events, I don't know what the outcome is going to be. That's a random process. Now, the first thing that we need to know to help us try to find probability is identify the sample space. We need to know everything that could happen if we're going to find the probability of certain events. So a sample space is literally just a set of all possible non-overlapping outcomes. A sample space could be infinite or finite. So let's look at some of the examples here that we've already looked at. So what is the sample space for rolling a die? Well, 1, 2, 3, 4, 5, 6. I could easily list the different things that could happen when you roll a die. Tossing a coin. I don't know what's going to happen, but I know you're going to get a tail or a head. Spinning a spinner with 5 colors. Well, it's either going to be green, it's going to be blue, it's going to be red, it's going to be yellow, or it's going to be navy blue. Whatever. I don't know what the colors are. But if I look at the spinner, I will know what the sample space is. Picking 3 boys out of a classroom. Now, this is going to be a little bit more complicated because there are so many different outcomes I got to think about with 12 boys, right? I don't want any of the 14 girls to get picked, but the 12 boys, I could get Maddox, Gavin, Daniel. Maddox, Gavin, Kelsey. Maddox, Gavin, Anthony. Maddox, Anthony, Clinton. I mean, I could sit here all day and start listing all the outcomes, but that would be your sample space. Now, taking a shower, that would be a little bit more infinite, right? I mean, I guess you could take a 1-second shower. I guess that's possible. And you could technically take a shower and just stay in there for 1,000 seconds. I mean, that'd be a really long time. So the point is like, I can't list all the outcomes there, but I mean, it's really too long of a list. And the same thing can be said for time to take to school. Like, you may know, I mean, you drive to school every day. You know that it typically takes 3 minutes, but maybe on a fast day, it takes 1.5 minutes. And maybe on a day with a lot of traffic or bad weather, it could take 20 minutes. I don't know. I can't sit here and list all those different possibilities. Approaching a red traffic light or a traffic light, it could be red. It could be yellow. It could be green. All right, I can list that. The sample proportion of smokers. I mean, if you think about it, that would be crazy weird, but with 500 people, maybe 0% of them are smokers. Heck, you might even get 100% of them to be smokers. But I guess a proportion could be anywhere in between. I mean, I haven't taken my sample yet. I mean, if it's a true random sample, I'm assuming there's going to be some smokers in there. And I'm also assuming there's going to be some non-smokers. But at the end of the day, I don't know what the sample proportion is until I actually go and do it. So that in itself is a random process. Now, the first couple of examples, I can actually list the sample space. That's when things are easy. So if all the outcomes in the sample space are equally likely, then the probability of an event E will occur is defined as the number of outcomes in favor of event E all divided by the total number of outcomes in the sample space. Now, it's also important to note the notation here. We use a P for probability, and then inside the parentheses, we write down the event that we're looking for. And typically, we'll abbreviate the event, or we'll just use like a capital E. Or if we're looking for what's the probability of getting a boy, like put a capital B there, something like that. But things are really nice and easy when your sample space is filled with equally likely outcomes. For example, what's the probability I roll a die and I get a 5? Well, on that die, there's only one side that's going to make me happy out of 6. So there's my probability 1/6. The probability of rolling a 5 is 1/6. What's the probability of rolling an odd number? Well, 1 is odd, 3 is odd, 5 is odd. So 3 sides of that die are going to make me happy. So 3 out of 6. So probability is pretty simple when you understand what your sample space is and they're equally likely. All right, now there are a few rules with this though, and they're pretty easy rules, but I just want to go over them. Rule number 1 is that the probability of an event is a number between 0 and 1, including 0 and 1. So you could have a probability as low as 0 and a probability as high as 1. Now, in terms of proportions, that would be 0% and 100% in terms of percentages, But a probability could be those or any other number in between. No such thing as negative probabilities and no such thing as a probability over 1. All right, the second rule is what we call the complement. The complement of an event is that event not happening. So if the probability of E is the probability of the event happening, then 1 minus the probability of E is the probability of that event not happening. And sometimes it's actually easier to find events by thinking about their complement. So again, pretty easy to understand that. Let's give a couple of examples of complement here just so you understand what I'm saying. So if event E is rolling a 5, then the complement would not be rolling a 5, which would be equivalent to rolling a 1, 2, 3, 4, or 6. So if the probability of event E rolling a 5 is 1 out of 6, well, the probability of not rolling an E, which we put like a little C right here for the complement, it's like a little superscript C. So that would be the not getting an E. Well, that would be 1 minus 1/6, which would be 5/6. Now, you actually don't need to do 1 minus 1/6. You could just count, hey, 1, 2, 3, 4, 5 outcomes will not be a 5, hence 5 out of 6. Either way, I'm going to get the right answer. All right, another example here is event W. Let's let event W be the probability of getting straight A's in your 5 classes. Let's say the probability of getting straight A's is only 9%, 0.09. Well, then the probability of the complement not getting straight A's would be 1 minus that, or 91%. Now, keep in mind, most people have no problem with the math, but make sure you understand, right? If getting straight A's is the event, not getting straight A's is at least one non-A. Like some kids think the opposite of straight A's is all failures. No, not at all, right? I mean, straight A's is A in all 5 classes. So the complement would be at least one of them is not A. Like, so if one of those is a B, I don't care if the others are A's, C's, D's, if as long as one of them is not an A, well, you didn't get straight A's. So the opposite of getting straight A's is not getting straight A's, which is at least one non-A. Another example here is the probability of it raining tomorrow. Let's say you watch the forecast and the probability of rain is 30% for tomorrow, or 0.30. Then you know that the probability of the complement not getting rain would be 1 minus 0.30, or 70%. Most of the time we don't even do the math. We just do the math in our head because it's quite easy. But that's complement. All right, last thing I want to leave you with here before we start looking at some examples is that probability, the definition, is really about repeated events, right? Make sure you really understand that probability is not about the short run. The probabilities of events in repeated situations can be interpreted as the relative frequency with which the event will occur in the long run. So just because we see something happen like a couple times in a row doesn't mean that it's going to keep happening in a row, right? It's the idea of the probability is not about the short run. It's all about the long run. You know, when we say, for example, that the probability of rolling a die and getting a 5 is 1 out of 6, That does not mean if I roll a die 6 times, one of them is guaranteed to be a 5. Absolutely not. Right? Some people actually think that, but that is not true. What that means is in the long run, after rolling that die countless and countless times, only then will I actually expect 1 out of 6 of the rolls to be a die, or to be a 5. And again, 1 out of 6 is really close to about 17%. And some kids will think that that means 17 out of 100 rolls are going to be a 5. Again, no. It means in the long run, after many, many tosses, only then would we expect about 17% of them to be 5s. All right, let's look at some of examples now. All right, at a basketball game, cheerleaders throw 50 miniature basketballs into the crowd. There are 13 blue, 20 red, and the rest are yellow or green. Suppose Gavin catches a basketball. What's the probability it's not blue? Well, the easiest way to answer any probability question is to consider your sample space. What could happen? Well, I could get a blue, I could get a red, or I could get a yellow, or I could get a green. Now, they told me that 13 out of the 50 are blue, 20 out of the 50 are red, and they told me that the rest of them, now if 13 are blue and 20 are red, well, then how many are left? Well, if I take 50, I subtract 13, I subtract 20, that means that 17 are left. Now, the question is, I don't know which ones are yellow, which ones are green, so I'm going to actually kind of have to combine those together. 17 out of 50 are either yellow or green. I mean, there could be 1 green, 16 yellow, or maybe there's 0 yellow and all 17 are green. I just don't know. But that's my sample space of everything that could happen. I wish I knew a little bit more for yellow and green, but unfortunately I don't. But the question says, what's the probability of not blue? Well, the probability of getting blue is 13 out of 50. So that means the probability of the complement not getting blue, remember we put that little C there for complement, not getting blue would be 1 minus 13 out of 50, and that would be 37 out of 50. So again, there's 2 ways I can answer this question. I could just count the blues. 13 are going to make Gavin happy if he catches it. 13 out of 50 are blue. That means that 37 are not blue, which is what the question asked for. Or, I could do the subtraction to get that. Or I could just simply say, hey, I don't want blue. Let me add up everything else. 20 red, 17 yellow, green. There's my 37 that are not blue. However you get it, you get it. 37 not blue. All right, another question here. A high school math club has 5 members, Aaron, Betty, Calvin, Doris, and Ella. 2 of them will be selected randomly to participate in the county tournament. What is the probability that Aaron and Doris get picked? Man, what's the probability Aaron and Doris get picked? This is a tough question. The only way I can figure this out is if I consider my sample space. I got to think about everything that can happen. And that's actually a little bit kind of complicated here. It's not that bad, but getting started is most important. All right, 5 members. I'm going to use their first initial to make this a little bit easier, A, B, C, D, and E. So let me think about everything that could be happening, right? We're picking 2 of them. So I need every possible sample of 2. So I could pick Aaron and Betty. I could pick Aaron and Calvin. I could pick Aaron and Doris. I could pick Aaron and Ella. Okay, let's see if there's anything else. I could now, I started with Aaron. Let's now start with Betty. I could pick Betty with Aaron. Oh, but wait a minute. Aaron, Betty, Betty, Aaron. That's really the same thing. I don't really care the order that they get picked. I just care that Aaron and Betty are picked. So I already listed Betty and Aaron. So let me think. Betty could be with Calvin. Betty could be with Doris. Betty could be with Ella. Okay, let's move on to Calvin first. Well, I already listed Calvin and Aaron. That was already counted right here. I already listed Calvin and Betty. That was right here. So those are just repeats. So let me go Calvin and Doris, and then Calvin and Ella. All right, now let me start with Doris. Well, I already listed Doris and Doris and Aaron. I already listed Doris and Betty. I already listed Doris and Calvin, so only one left is Doris and Ella. And then since Ella's at the end, well, she's actually already been with Aaron, Betty, Calvin, and Doris. No reason to list any others. So that's actually 10 total outcomes. My sample space has 10 different options. All right, now, how many of them are what I'm looking for? I'm looking for Aaron and Doris. Well, only one outcome is going to make me happy. The only one outcome that makes me happy out of 10 is Aaron and Doris. So there's my probability, 1/10. Really, really simple. So the point is, if you know your sample space, probability is quite easy. Let's do another one. A fair die with its faces numbered 1 through 6 is tossed. What is the probability that the side landing face up is greater than 4? And explain what this probability means using the probability definition. All right, so let me list my sample space. I always start there. 1, 2, 3, 4, 5, 6. Those are the outcomes. They want me to find the probability that the die is greater than 4. Well, the only numbers greater than 4 are 5 and 6. So 2 out of the 6 options in my sample space will make me happy. And that reduces to 1/3. So what does this mean in terms of probability? Well, it means that in the long run, after many, many, many tosses of my die, only then would I expect 1/3 of them to be a number greater than 4, or only then would I expect 33.33% of them to be a number greater than 4. It does not mean that 1 out of my next 3 tosses will be a number greater than 4. It does not mean that 2 out of the next 6 tosses. It does not mean that 33 out of the next 100 are going to be greater than 4. No. Probability is all about the long run. Please get that straight now. So only after many, many tosses will I actually expect to see 1/3 of them be greater than 4. All right. The probability that after a randomly selected phone number is called, the person who answers will participate in a survey is 30%, 0.30. So when a random phone number is called, there's a 30% chance that the person will answer the survey. Kevin interprets this as meaning that of the next 20 numbers, 6 will participate in the survey. Is he correct in his thinking? All right, well, let me get a couple things straight here. There is a 30% chance that somebody will answer the survey. Common sense means that 70% chance they will not answer the survey. So that's my sample space. Yes and no. Pretty easy sample space. Now, Kevin says that of the next 20 calls, 6 will say, yes, I'll participate in the survey. Now, 6 divided by 20 is 30%. But that's not correct thinking, Kevin. Remember, 30% yes is only in the long run. 20 phone calls is not the wrong one, Kevin. Come on, Kev. The idea here is that just because you have, if you think about it, with 20 phone calls, you could get 6, you could get 7, you could get 8. Who knows? It's a short run. 20 phone calls, too short. Only in the long run, only after looking at many, 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 many phone calls will I actually see 30% of them say, yes, I'll answer the survey. All right, next question here, final question. A jar of 300 jelly beans, 60 are red, 120 are green, 30 are yellow. 1 jelly bean will be selected at random from the jar. If each jelly bean in the jar is only one color, no double color jelly beans, what could the probability of getting an orange jelly bean be? Now, at this point, you might be like, what? Orange jelly bean? Didn't mention orange jelly bean. Well, let's consider my sample space. I have 300 total jelly beans. I know that 60 of them are red. I know that 120 of them are green. And I know that 30 are yellow. Okay, so let's see here. 60 out of 300, that is a 20% chance of randomly getting a red one. 120 out of 300 is a 40% chance of randomly getting a green one. 30 out of 300 is a 10% chance of randomly getting a yellow one. So if I were to pick jelly beans over and over again, right? Like pick one, put it back, pick one, put it back. In the long run, 20% of my picks would result in a red one, 40% green, 10% yellow. Now the question is, what about orange? Well, most kids are just going to jump and say, well, 20, 40. That's 70% thus far. So that means orange is 30%. Well, maybe. The question is this, could be orange. I don't know. Are there any other colors in there? It didn't say, but I don't know. Maybe there's purple. Maybe there's black. Maybe there's blue. I don't know what other colors are in there. But here's the deal. There could be all oranges. Maybe all the remaining jelly beans are orange. In that case, then the answer, yes, would be 30% are orange. But maybe it's a trick question. None of them are orange, so there could be 0% orange. So the idea here is, because I really don't know what's left in my sample space, I only know red, green, and yellow. The rest of the sample space is kind of a big question mark. The only thing I can conclude about orange is that it's somewhere between 0 and 30%. It certainly can't be more than 30% because that's already all been covered for with red, green, and yellow. It definitely can't be less than 0% because you can't have a negative probability. So somewhere between 0 and 30% is the possible probability of getting orange. But since I can't complete my sample space, I can't give a solid answer. So if you look back at the examples that we've done, and if you have any confusion, I would definitely recommend going back and re-listening to them. The common thing is this: list your sample space. Think about everything that can happen, and then calculating probability is usually pretty easy. Now, in the next couple of videos, we will get into some more difficult probability, but if you could list your sample space, boy, life is easy. You know, if we think about an example where it's kind of impossible, like, for example, how long could I take a shower for? I mean, I can't list my sample space. I mean, it's just too big. So if I said to you, hey, what's the probability you're going to take a shower over 10 minutes? I mean, I can't answer that because, I mean, what do I divide? I mean, the only way to answer that question, what's the probability you're going to take a shower over 10 minutes, is to actually just take a bunch of showers day after day after day. And I'm going to keep a notebook, right outside my shower, right by my sink. And every time I take a shower, I'm going to note how long it took. 5 minutes and 30 seconds. 9 minutes and 22 seconds. And after many, 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 many days of writing down how long my shower took, then I would actually go back and count how many of them were over 10 minutes. And then I can get an estimated probability. But without being able to list my sample space, sorry, it's really difficult to find probability. So enjoy the video. Hope it was pretty easy to understand. Get ready to practice some problems and get ready for the next video.